And here we'll move on to the last bit of lecture on mining frequent item sets. So to review, of the 5 learning objectives for this module, the last 2 here are about providing applications for frequent item set mining and then explaining the connection between frequent item sets and counting pairs. Before we get into these though, you might ask, well, why are we talking about frequent item sets in a data mining course? And why are we using this as like really our first foray into data mining? And the answer is this question of finding frequent pairs or identifying things that occur together shows up many different times in our course. If we're looking for whether 2 items are similar, often similar items will co-occur, or how we identify or measure similarity that leads to a co-occurrence idea. If we're looking at networks or social networks or networks in the internet, and we try to identify clusters or groups of people who are often connecting or interacting with each other in communities, these communities also make up nodes that often co-occur. If we're trying to recommend new shows or new videos or new songs or new products, one way to do this would be to look for products that occur with some high frequency with other products you've already purchased. So by looking at your purchase history or looking at your viewing history in YouTube, we can say, well, if you've watched these things, what is a new YouTube video that will often co-occurs with these videos that you've already watched? Same thing with search. We can look for pages that co-occur frequently with a particular query as a way to return pages that are relevant to a particular search interest you have. So as we move into this idea of frequent item set mining, let's talk briefly about some terminology. An item can be really anything, some abstract thing, and a collection of these items is referred to as an item set. When we talk about baskets, which you'll see examples of here in a few minutes, this idea of a basket generally refers to some collection of items in some small transaction. So when we talk about the market basket analogy, you can think of these as items that get grouped together based on some action or behavior. So I bought a number of items in a basket, or I watched a set of YouTube videos in one session. That is a basket of YouTube videos. Or I interacted with these 5 user accounts in one session on Twitter. So those transactional sets of items we refer to as baskets. And the connection between items and baskets is really this many-to-many relationship. An item can appear in multiple baskets, and a basket can contain multiple items. So for the question of frequent item set mining, really what we want to do is identify items that often appear together. Now the real-world example, the sort of apocryphal example, is the supermarket problem, or the market basket model, where we have a bunch of items that are bought together by many customers, and we want to identify things that are frequently purchased together, where a basket in this case is the set of items that I have purchased. The approach here is that we get huge amounts of data about these individual transactions. People have purchased some set of items every time they go to the store. Generally these baskets, these sessions of purchases are small. When you go to the store, you don't buy everything in the store. When you go to Amazon, you don't buy everything on Amazon. And in the supermarket or market basket context, there's this set of apocryphal rules that you hear about. One is that people who buy diapers and milk very often are likely to buy beer. Again, this is a standard sort of apocryphal example that you see in many kinds of studies of this example, but this allows supermarkets to do some optimization here and say, well, if the diapers and milk are together and we want to get people to buy a particular product, in this case beer, then we can locate the beer next to the diapers and milk, so when a customer comes and purchases diapers and milk, they'll see the beer there. They're already more likely to buy it based on the data that we have, so then they're more likely to pick it up and make this purchase. Alternatively, milk and bread are very commonly bought items, and they're often bought together. So another way a supermarket can exploit these kinds of behaviors is to separate these 2 staple items. Put milk on one side of the supermarket and bread on the other, and these are staple items as opposed to beer, which is a non-staple item. People will have to go from one side of the grocery store to the other to purchase their milk and bread, meaning there's more opportunity for them to spend time in the grocery store and purchase more items. In the same way that YouTube is interested in keeping you on the platform, Facebook is interested in keeping you on the platform, these grocery stores are interested in keeping you in the grocery store for some amount of time to increase your odds of spending more money. So in this market basket model, we have a large set of items. This is the full stock of the store, or Amazon's full stock. And we have a large collection of baskets, where each basket is this small transaction of things that I purchased in a particular trip to the store. And generally you have many instances of these baskets. And these baskets are non-unique. You can have, well, today I went to the store and bought milk and diapers. Next week I have to go to the store again and buy this. Last week I went and bought cat food, and I'm consistently buying cat food. These baskets can occur many times and have lots of the same kinds of content in them. And what we want to do with these baskets is discover rules of association. Basically, the idea that people who bought some set of items are more likely to buy another set of items. Can we identify or construct these rules such that when somebody purchases these three, or is going to purchase these three items, we can then know what to suggest or take action on. What else are they likely to buy from a predictive case? So for example, here we have a set of items. These are 5 items: bread, milk, Coca-Cola, beer, and diapers. And we have these 5 baskets, these collections of items. So the first basket has bread, Coke, and milk. The second basket has beer and bread, etc. And the rules that you might discover from this data are that people who buy milk very often buy Coca-Cola. Because if you look at the baskets, of the 4 baskets that contain milk, 3 of them also contain Coca-Cola. And then the example we said before, of all the baskets that contain diapers and milk, those baskets also contain beer. So those might be rules you could extract from this data. So these association rules in general are useful, and we set them up as a set of if-then statements. Essentially, if you bought these set of items, I sub 1 through I sub k, that the likelihood or the probability that you're going to buy this jth item or this jth set of items is increased, or is more likely than not. And we can use this for all kinds of things, from personalization. We want to have YouTube show you videos that you're more likely to watch, for recommendation. Netflix wants to recommend new movies to you, or for advertising, we want to put ads in front of you that you're likely to click. Some examples of this: if we consider items as products and baskets as these transaction of products that we bought in a particular trip to the store, as we have been, then we can use this information to do what's called offsetting price. That stores have terabytes of data, petabytes of data about what customers have bought, and they can use this data to do the things that I've already mentioned, such as placement of beer next to milk and diapers, or spreading out of milk and bread. This is all about better positioning, right? So we can better position tempting items like beer, but we can also do some trickier things. So say we run a sale on a particular staple item. We don't want to lose money, so we want to increase the price of items that are bought with the staple item. So we can run a sale on diapers, we can do markdown or discounting on diapers, but as a store, we can offset that by increasing the cost of a non-staple item like beer or some consumable along those lines. But crucially, we want to make sure that this association rule occurs frequently enough that the amount of money we are losing on discounting our staple good is offset, hopefully completely, by our increase or markup on our non-staple item, or our association rule item. Other kinds of places where this approach is useful, another example is side effects in drugs. So instead of items being the things we could purchase and baskets being these transactions, we can think of items as drugs and the collection of side effects that they might have. And baskets are patients, or the collection of patients and their associated drug prescriptions and their reported side effects. Then, by looking at things that occur frequently, drugs and side effects that occur frequently in these baskets, we can identify association rules that connect drugs to particular side effects. So for instance, our item set might include 3 different drugs and 3 different side effects. we have a number of patients who have taken a particular drug and reported some set of side effects. So this first patient took drug X, reported side effects A, B, and C. Next patient took drugs Y and Z, reported no side effects. And a third patient also took drug X and only reported side effect A. By looking at this connection of items and baskets, you could identify that perhaps drug X appears more frequently with side effect A. In some large scale, this would give us some idea that there is some association between drug X and side effect A. Similarly, you could do this with community detection, where you have a slightly different view of this. Instead of items being products or drugs and side effects, we can think of items as neighbors in our graph or our social network, and our baskets are now the sets of people individuals are friends with, or our friend group. And that's how we group people together based on their friend and follower lists. So in this case, we can look for groups of accounts that occur frequent or that co-occur frequently. So we have some bipartite graph here of S nodes and T nodes that are split into these two layers. And what we want to do is take each user in our data set, break them up into, or decompose them into their sets of friends to create our baskets, and explicitly look for sets of friends of a particular size that occur more often than some threshold S. And this gives us a way to group communities together, group these, or extract these frequently co-occurring groups of friends. The issue here when we talk about mining association rules, so hopefully I've shown you that association rules have value, but the issue is that there are too many association rules given a particular set of items to enumerate them all and evaluate whether these association rules are useful to us. So just an example, if you have some set of items of size D, we get huge numbers of possible association rules. In fact, this is exponential with respect to D, so even if you have, in this example, 6 different items, we already have 600 different rules, and this blows up very quickly. So given that, how can we be intelligent or clever in our identification of association rules? By identifying and then evaluating only those ones that we may actually care about, only those association rules that are interesting to us or occur frequently enough for us to find value in them. So we can do this by finding sets of items that frequently co-occur together, or identifying these frequent item sets. So what is the real question here for identifying frequent item sets? This is a simple question of which sets of items or subsets of items in our collection frequently appear together in baskets. So we have a couple of metrics that we can introduce for this. The first is support. The support for a particular item set I is defined as the number of baskets containing all the items in I. Similarly, we have a threshold on S, so we can threshold S and say anything that occurs, or any item set that occurs more than this threshold S is, in some sense, a frequent item set. So we can specify our support threshold and then identify things that are frequent as things that occur more often than that threshold. So if we go back to our example of our 5 items, bread, Coke, milk, diapers, and beer, we can see that the support for the item set beer and bread equals 2, so it occurs in 2 of these baskets. We see it in basket 2 and basket 4. So we can say its support is 2, or we can normalize that by the number of baskets we have and say it's 2 over 5 or 0.4. So if we have some example here where we have 5 different items and 8 different baskets, we can specify some support threshold here as being 3, so anything that occurs, or any item or collection of items that occurs 3 or more times, we will say is a frequent item set. Now item sets can be more than one item, but they can also be a single item. So we see here that there are 4 frequent single items: milk, Coke, beer, and juice. But there are also frequent pairs of items. So milk and beer, beer and Coca-Cola, Coca-Cola and juice. All of these things occur more than 3 times. But there are many other collections or many other pairs that occur fewer than 3 times. And we hopefully don't want to count all of them. And we'll talk about how we can get around this counting. But these are the ones that we care about, the ones that are frequent or occur with some threshold of support S. So when we talk about mining association rules, we have to deal with the fact that there are many association rules, and we want to identify ones specifically that are interesting. How do we measure whether an association rule is interesting? So the first metric we'll introduce is this idea of confidence, that the confidence is the probability of a particular item being purchased or showing up in a basket given all these other items. So the rule is this item set I sub 1 through I sub k, if those occur in your basket, this jth item is also highly likely to occur in your basket. And we can evaluate or calculate this metric just as a ratio of support. This is just the fraction of the baskets that include I and j over all the baskets that include I. But that's not necessarily enough for our idea of interesting. It's just because a rule has high confidence doesn't make it particularly interesting for us. And the good example is, in our market basket model, just because there is an association rule saying these items occur frequently with milk doesn't necessarily mean that that's interesting, because there are two interpretations here. One is that milk is in fact bought often only with this set X, which means we should explore that or use that association rule. Alternatively, milk may just be bought very often. It doesn't matter what other items it's bought with, it's just one of the most commonly bought goods. So the connection actually is not, there's some sort of correlation here between the presence of X and the presence of milk, but it's not necessarily driven by the actual presence of X. So we can introduce a new metric, or an additional metric called interest, which is just the difference between the confidence of this association rule I to j and the probability of seeing that jth item. So if the confidence of our set X and milk is high, but the probability of purchasing milk is also high, then our interest should be low. Now generally what we see is rules that have a high absolute value or an absolute value above 0.5, those are the interesting rules. If you remember your probability theory, another way to look at this is whether the probability of j given I is equal to the probability of j. So if those two values are the same, in fact, that j's presence is in fact independent from I, then interest is 0. So we can actually run an example of this. We'll rewrite our confidence and support equations here, and we want to evaluate the interest for this association rule of if you buy milk and beer together, you are highly likely to buy Coca-Cola. So the confidence of this association rule is the support of the triplet milk, beer, and Coke, which occurs in two baskets, basket 1 and basket 6, divided by the support of just milk and beer, which is 4, because that occurs in basket 1, basket 3, basket 5, and basket 6. So our confidence here is 0.5. But if we look across all of our 8 baskets, we see Coca-Cola appears in 5 of these 8 baskets, so a little bit over 0.5. And the interest is the difference, the absolute value of the difference between these two, which is small, about 0.125. So this is a not interesting or an uninteresting association rule. And we can evaluate any association rule using this method. So evaluation of association rules and whether they're interesting is not hard. This means that the problem here is to find all the association rules that have this high level of support and high confidence. So really this boils down to finding things that have high support or finding things that are frequent, or these frequent item sets. And we can demonstrate this by splitting the association rule mining task into 2 steps. Say that we actually already have all of our frequent item sets given a set of baskets. We'll say that we do this magically for now. We'll talk about how this is done in a second. Once we have those frequent item sets, though, we can generate our association rules relatively quickly. Basically, given every frequent item set in our collection, we look at all the subsets of this item set, and we know that since those item sets are frequent, all the subsets of that item set must itself also be frequent. That means, or once we have that intuition, we can evaluate all of these association rules by taking subsets of our item set, and for every subset that we have, we can split this rule into that subset implies the all the other items in that item set minus that subset. And then we can evaluate the interest for this rule. Given the items in our subset, what's the likelihood, or what's the probability that you will then purchase these other items that exist in this frequent item set without the items, or without these A set of items. So it's pretty straightforward to generate and evaluate these rules given a small set of frequent item sets. And then we just output the ones that are above our threshold. So if the difficulty is finding frequent item sets, how do we do that? Well, we'll quickly set up a model for this. Assume that we have this very large collection of baskets stored on disk somewhere, and the baskets themselves are relatively small. So we may have a huge set of items, but the number of items in any particular basket should be on average quite small. As you can imagine, when you go to, as I mentioned before, you go to the grocery store, you don't buy everything in the store in one transaction. You go to the store many times, so over a year you might buy many of the store or much of the store's inventory, but in individual trips you don't buy everything. Same thing with Amazon. In individual purchase sessions on Amazon, you don't buy everything from Amazon or everything that they have. You buy maybe topically oriented or task oriented things. Same thing with YouTube. You don't watch all the videos on YouTube in a given session. Sessions are generally relatively short. Maybe you watch some small collection of videos, leave YouTube, and then come back several hours later and create a new session. And these sessions are our baskets. So in general, we assume that baskets are small. Given this context, we can show that really the hard problem about, or the hardest part about finding frequent item sets reduces to finding frequent pairs of items. And you can see this in a couple of different ways. So first, frequent pairs are way more common than frequent triples. In this context where baskets are small, there's lots of opportunities for us to generate pairs, but as we increase the size of our frequent item sets, they necessarily have to happen fewer and fewer times because, as I said, on average our baskets are small. You can actually check this out in the data. If you had realistic data here, that the probability of being frequent drops exponentially as the size of your item set increases. Again, as a implication of our baskets being small. Also, there's a connection between the frequent triples, frequent quadruples, and so on, and the frequent pairs. And this connection is any item set that is frequent must have all of its subsets be frequent. This has an inverse implication for it, that if any subset of a particular triple or quadruple, etc., is infrequent, that original set must also be infrequent. So we say this here as a triple containing an infrequent pair is also infrequent. So the only triples we care about are the triples that contain frequent pairs. So let's first focus on this idea of frequent pairs, and then we'll extend to larger sets. So in order to count frequent pairs, though, or frequent item sets in general, we need to look at all the item sets and count them. That the only way we could know whether an item set is itself frequent is if we have somehow counted that item set. The issue, though, is that there are too many item sets to count in a scalable way. So how do we count the item sets or be clever about the item sets that we count, such that the effort we expend or the computational time and space that we spend is used to only count the ones that turn out to be frequent? And we can do this in a clever way. But first, let's talk about some naive ways. So a simple way may be to read through the set of baskets and count all possible pairs. So you just look at every possible item in the data set, create this square matrix, and count, well, how often do these two items co-occur? It's a symmetric matrix, so we can do some cost savings and only deal with the bottom left or top right of the matrix and count half of them, but we're still talking about some quadratic here about all pairs of items in our data set. For some back of the napkin math, we can show that even for small numbers of items, this has a pretty significant memory footprint. It can very easily exceed main memory even with small numbers or relatively small numbers of items. So for instance, say Walmart has 100,000 items. We do some back of the napkin math to say each count that we maintain is a 32-bit integer, or 4 bytes here. So we're talking about approximately 20 gigs of RAM needed just to store all pairs or counts of all pairs of these 100,000 items. And certainly Walmart now with online stores has way more items than that. So we're talking about, in a naive way, spending 20 gigs just to count all these pairs. And to make things even more frustrating, probably the vast majority of these pairs in our matrix are zeros, that they just never occur together. For example, no one ever buys Coke and Pepsi together, or no one would buy the new movie Cats with something like Schindler's List or The Godfather. Why would you buy a really terrible movie and a great movie together? So there's going to be a lot of instances of zeros in this matrix that we're spending space in memory actually just holding. So we try and get a little bit better than this. Rather than storing all possible pairs, we can store every possible count, but only those that we see. So you scan through your list of baskets, generating pairs as you go, and then for each pair that you see, you do some hashing or a hash table, or you generate this 3-tuple and say, well, we see item 1, we see item 2, and we maintain a count of that. So then that count is only these non-zero elements. So we go from this triangular matrix that we have to fill out to what's called a sparse matrix, where we only keep track of these non-zero elements. Now we pay some penalty here, so in that first triangular matrix, we don't have to maintain RAM for these, or memory for these item 1, item 2 lists. We only have to maintain memory for the count. For the sparse matrix approach, we need to maintain 3 different values here: IDs for item 1, ID for item 2, and a count of the times that we see those things. But that's still somewhat better. We can see that this triangular matrix approach is n squared in size, and the approach 2 works better as long as fewer than a third of our possible pairs actually occur. That's fine, but still we're only talking about a relatively marginal reduction in memory footprint. So if we have many, many pairs, still this is going to be problematic if the number of pairs that occur could be large. So what we see here, in both cases, the necessary memory we're still talking about is order d squared. And while I said many of the instances in our matrix, our count matrix, are going to be 0, we can go even further than that and say, well, not only are many of the pairs going to be 0, of the pairs that do occur, many of those probably only occur one time. You can see this in a number of real-world instances, like in social networks. How often do you interact with many sets of people? You interact with some small group of people a lot, and a large group of people very seldomly. Maybe there's one person, or a large group of people rather, over the course of your lifetime that you've only ever met once and then never again. Is it really valuable to maintain those additional, or records of those additional single instances of interaction? Those instances where 2 items were purchased together once and only ever one time. So we end up with a lot of space allocated just to storing these pairs that occur very rarely. So we can get around this using the A-Priori algorithm, which is one of the most cited algorithms in computer science, and it tries to do this in a clever way by using 2 passes. And the main idea that it exploits is this one that I've mentioned several times. If an item set is frequent, every subset of that item set must also be frequent. The contrapositive for this is if a particular item is infrequent, no item set that includes that item can then be frequent. So that means anything that we've identified, any single item that we've identified as being infrequent, we no longer have to maintain any pair, any triple, any quadruple, etc. of that that includes that item. So now we can remove all those instances, or remove many instances of these rare associations, these rare pairs that we know will never become frequent sets. And this can lead to huge savings in the amount of memory we need. So let's break down how the A-Priori algorithm does this. So in the first pass, we go through all of our baskets, counting up the frequency of each individual item. We can do this in memory proportional to the number of items in our set, this value d that I mentioned before. And items that appear more frequently than our threshold, we say those are frequent items, and then we throw away all other items that we've identified as being infrequent, because now we know that any pair, including an infrequent item, must be an infrequent pair. This allows us to then generate all pairs of only frequent items, so only these g sub i's, and when we scan through the baskets again, we do the second pass, we only count pairs that are composed of elements from this subset gi, or from the subset g of frequent items. So now we have similarly square matrix, or triangular matrix here, but rather than it being in d squared space, we need to do it in g squared space. And g generally has far fewer items in it than the full item set, so g squared is going to be much smaller than the d squared set. So when we actually pass or implement this in code, what we end up with is significant cost savings in memory, and saying even only if 10% of our items are frequent, which is a relatively high threshold, we're still experiencing 2 orders of magnitude less memory use. So there's a real value here. So let's generalize this to triples, quadruples, etc. So in pass 1, we scan through our list of baskets, counting the frequency of all items in our set. So we count this up, and then we filter out the items that are infrequent. Now we can construct all pairs of items, this L1 set that contains all pairs, where these pairs are composed of items that are themselves frequent. So every item in this set L1 has the possibility of being a frequent pair, because it's only composed of individual items that were themselves frequent. Now we count up all of those pairs in another pass, throwing away any pair that is below our threshold of support, and now we can create a new potential candidate set of triples by taking the product of our L2 pairs and our L1 frequent singles. So now any triple we get has to be composed of a frequent pair and a frequent individual item. So this means we start with this large matrix of pairs, this L1 by L1 matrix, and in this next step where we go to potential triples of the individual items crossed with the pairs of items, this individual, or this L1 times L2 matrix tends to be a good bit smaller than this L1 times L1 matrix, that our majority of our memory is used in computing this L1 by L1 matrix, all the counts of all pairs that are potentially frequent. Because as I mentioned before, the longer your item sets become, the less likely they are, the more rare they are to occur in a frequent way. So this L2 generally is much smaller than L1, so the largest memory component here is this counting of frequent pairs. And as you get further out or longer in the item sets, your memory costs decrease. So to repeat, why are we talking about this? Why are we talking about frequent item sets? Well, they give us a baseline or a foundation for the kinds of tricks or revisions of the problem we can employ to try and be more sophisticated or more efficient in the way that we handle these kinds of issues, where we have very large sets of data. Because we're talking about web scale data, seeing large sets of data is very common. You can very quickly get huge amounts of data on Twitter, on Reddit, on many other data sources. It can quickly become gigabytes, terabytes without a huge amount of time. Now, at the same time, when we talk about these methods for dealing with large-scale data, it's worth keeping in mind this adage from Knuth about premature optimization being the root of all evil. In many cases, we don't want to try and eke out very small increases or incremental increases in performance. What I want you to get from this class is there are different ways to look at these problems that allow us to get substantial cost savings just by being intelligent about what we have to count or the things that we have to include. So this moneticity idea that every frequent item set must also have all of its subsets as frequent item sets allows us to filter out many instances of, or many possible item sets that will never have a chance of being frequent in our context or given some particular threshold. So that can give us huge cost savings only by being intelligent about how we look at the problem. All right, so this is going to round out the end of Module 1. We've talked about item set mining, talked about its applications, a number of different example applications that will show up across this course, and I've given you some insight about why counting pairs of items is crucial to identifying frequent item sets of arbitrary size. So that ends it, as I said, for Module 1. If you have any questions about it, you can post in the Module 1 discussion forum or come visit me during office hours.